Okay, let's dive right in. Welcome to this explainer. Today, we're tracing one of the most incredible, mind-bending scientific journeys in human history, cracking the code of the atom. For centuries, this was just pure theory, But uncovering its actual physical structure, that became the ultimate detective story.
But before we get into the weeds, I want you to ask yourself something. Did you truly know what makes up the physical reality of your own body? I mean, we walk around feeling incredibly solid, right? You knock on a desk, it feels rock hard. But as we unpack this science today, your perception of reality is going to be severely challenged. We're about to see just how solid matter really is.
It took generations of scientists piecing together clues from complex chemistry and physics to finally solve this atomic puzzle. We're talking everything from early lab experiments with glowing discharge tubes and prisms, all the way to complex quantum equations plotting 3D probability clouds. No single genius figured this out alone. It was essentially a multi-generational relay race of the mind, with each scientist passing the baton, slowly illuminating the microscopic universe for the rest of us.
So let's hit Chapter 1, Meet the Subatomic Particles. To really understand the atom, we've got to meet the main cast of characters, and honestly, the sheer difference in their scale is staggering. Take the electron, discovered by J.J. Thomson back in 1897 using a cathode ray tube. Just look at that mass, 0.00546 atomic mass units. It is wildly lighter than the proton, discovered by Goldstein, and the neutron, which James Chadwick found much later in 1932. To put that into perspective, an electron is about 1,837 times lighter than a proton, and yet somehow it carries a negative charge that exactly balances the positive charge of that heavy proton. These three fundamental particles, they're the core puzzle pieces our scientific detectives had to work with.
Moving on to Chapter 2, Shattering the Sphere.
Now, atomic theory is essentially a story of continuous, messy improvement. Every scientist found a brilliant clue, but they also left a glaring plot hole for the next generation to fix. The whole thing kicked off in 1808 when John Dalton thought the atom was just an indivisible, solid sphere. Then Thomson found the electron and pitched his plum pudding model, basically a positive sphere with negative electrons jammed in it like fruit in a pudding. But yeah, that didn't last. Rutherford came along in 1911, discovered the nucleus, followed quickly by Bohr's orbits, and eventually Schrödinger's wave equation. Each massive step forward literally shattered the accepted reality of the step before it.
We really need to talk about Rutherford's contribution here because it's absolutely mind-blowing. He fired high-speed alpha particles at an ultra-thin gold foil. We're talking just 10 to the negative 4 millimeters thick. He totally expected them to blast right through Thomson's soft plum pudding atom. But a few of them bounced right back. This revealed a completely unimaginable scale. The nucleus is 10 to the negative 15 times smaller than the total volume of the atom. Think about it like this. If the atom were a massive football stadium, the nucleus would be a tiny fly sitting right on the 50-yard line. The rest of it, literally just empty space. But Rutherford's model had a massive plot hole. According to classical physics, specifically Maxwell's theory of electrodynamics, a charged particle moving in a circular path should constantly emit radiation and lose energy, which means if an electron is orbiting a nucleus, it should instantly spiral inward and crash. By those rules, the atom literally shouldn't exist. This massive contradiction is what prompted Niels Bohr to step in around 1913. He argued that electrons actually live in quantized, stationary orbits where they mysteriously just don't lose energy. And that totally saved the atom from theoretical collapse.
Which brings us to Chapter 3, the quantum plot twist.
Our first major twist actually comes from light, thanks to the photoelectric effect, which was beautifully explained by Albert Einstein. See, when light hits a metal surface, it can knock electrons loose, but only if that light hits a specific minimum threshold frequency. This meant light wasn't just a smooth, continuous wave like everyone thought. It acts as discrete individual packets of energy called quanta, or photons. This was a real game changer. Energy itself was quantized, delivered in distinct, unbreakable little chunks.
So, if light can act like a particle, could matter act like a wave? Well, in 1924, Louis de Broglie proved that yes, electrons do actually behave as both particles and waves. This dual nature led directly to Werner Heisenberg's famous uncertainty principle. It states you simply cannot know both the exact position and the exact momentum of an electron at the exact same time. It's kind of like a cosmic speed camera. If it snaps a perfectly sharp picture of exactly where a car is, the blur vanishes, and you have absolutely no idea how fast it was going. But if it captures the speed perfectly, the car is just a blur.
and you don't know exactly where it is.
And that brings us to the ultimate plot twist in our story. Scientists realized they had to completely abandon Bohr's neat classical 2D planetary orbits and embrace the frankly mind-bending reality of the quantum model. Electrons do not travel in clean, predictable circles. They exist as chaotic 3D probability waves and clouds around the nucleus. We literally can't say exactly where an electron is, we can only say where it is most likely to be.
All right, let's look at Chapter 4, Mapping the Invisible.
By solving Schrödinger's wave equation, we get this incredible tool, a set of 4 quantum numbers. You can think of these as a set of cosmic coordinates for the electron. Just like finding your friend's house requires a country, a city, a street, and a house number, finding an electron's probable location requires these 4 specific markers. You've got N, the principal number that dictates size and energy level, then L, the azimuthal number dictating the subshell's shape. M dictates the magnetic orientation in space, and S tells us the electron's spin.
Now, that L quantum number, it dictates some truly bizarre 3D shapes for these electron clouds. The s orbital is a nice, simple, symmetrical sphere that holds up to 2 electrons. But the p orbital looks like a dumbbell holding up to 6. The d orbital gets even weirder, shaped like a double dumbbell that can hold 10 electrons. And the f orbital is so mathematically complex in its shape it can hold 14. But remember, these aren't solid containers. They're just the 3D zones where an electron is mathematically likely to just pop into existence.
Next up, Chapter 5, Cosmic Traffic Laws.
All this electron traffic follows 3 very strict rules, almost like a highly regulated board game, to maintain order and stability within the atom. Step 1 is the Aufbau principle. Electrons are basically lazy. They will always fill the lowest energy orbitals first. Step 2 is Pauli's exclusion principle. No 2 electrons in a single atom can have the exact same 4 quantum numbers. If they're sharing the same orbital, they absolutely must have opposite spins. And step 3 is Hund's rule. When you have equal energy orbitals, like 3 empty p orbitals, electrons prefer to spread out and occupy them singly before they're forced to pair up and repel each other.
But you know, nature is a bit of a rebel, and it deeply, deeply loves symmetry. Which brings us to our famous rule breakers, chromium and copper. Based on the traffic laws we just talked about, you'd expect a very specific configuration. But chromium actually shifts an electron to create an exactly half-filled d subshell. Copper does something similar, shifting one to create a completely filled d subshell. Why? Because that symmetrical distribution and the release of exchange energy among electrons with parallel spins creates a state of extra stability. So even at the weird, chaotic quantum level, balance really is everything.
To wrap up this incredible explainer, I want to leave you with a pretty profound thought to ponder. We started all of this by asking how solid you really feel. Well, we've seen that atoms are overwhelmingly just empty space. And the tiny bits of matter that do exist, the electrons, they don't even have a fixed location. They're literally just vibrating waves of probability governed by these complex, abstract quantum rules. So, if the very building blocks of your body and the screen you're looking at right now are just probability clouds, how solid is the reality you experience every single day? It's a crazy question, right? One that started with a crude glass tube in the 1800s and continues to challenge our absolute brightest minds today. Thanks so much for joining me on this explainer, and remember to keep questioning the universe around you.